Okay, hi everybody. Welcome back to our political statistics class. This is our final week. This is the seventh lecture, and we have reached the end of the course of the class. And I really want to thank you for this amazing journey. I think that this class has equipped you with relevant and new skills and relevant skills to conduct research in political science. So I'm very happy with this. Okay, so a couple of announcements. And the first one is that for this lecture, we're going to have kind of a small or kind of a short, or kind of brief lecture, in conceptual lecture. And this is going to be the final inferential method that we're going to learn. That is, this is going to be the introduction to linear regression. And I hope you have the chance to use it in the final project, but you don't need to do it. You can do it if you are using a dependent variable that is numeric. Otherwise, you cannot do it. But it's an amazing method. It's going to be very useful for you guys. And even if you don't use it for this class, try to use it in the future, because it's one of the most is the basic foundation of all other methods in advanced statistics, in social science in general. Okay, so we're gonna have a simple and short quiz based on this lecture, and also we're gonna have a lab. We're gonna learn how to prepare figures in R with three variables, with 2 and 3 variables. And the idea is that you need to prepare the figure that is relevant for your applied project. So everything that we're going to do is going to be focused on that applied project right now. Okay. So you're going to do it, and that's going to give you a chance to make improvements for the final project. If the figure is fine, so you don't need to do any improvement. So you just copy paste and put it in the final project, and you're done. So you have that part of the applied project done. Okay. And if you had problems with the figures, you have the chance to make improvement. I'm gonna help you to improve that figure for the final project. Okay. Okay. So this class, as I said, we're gonna learn the Swiss Army knife of quantitative research methods. The linear regression is the most basic, but at the same time not the most powerful, but the most flexible method that we have learned so far. And yeah, compared to the other methods, this is the most powerful. It is very basic. So based on the linear regression, you have all other methods such as generalized linear models, multi-level models. So it's very important that you learn this foundation of political statistics. Okay. This is where we are right now. This has been the class, and last 2 lectures we learned how to use this idea of the standard error or the random sampling error, and the implications of the central limit theorem and normal distribution to conduct inferential statistics, right? In the lecture 6, I taught you how to use or how to conduct tests of significance and measures of association for bivariate simple analysis. And this week we're going to learn a method that you can use not only to tell you or to test the significance of a relationship, but also that is going to give you a measure of the strength of that relationship and the sign of that relationship. Okay. And also the linear regression help you to deal with threats to internal validity. So you can include here additional factors or variables that potentially can affect your relationship of interest, the relationship between X and Y. Okay. Okay, so let's talk about first the bivariate linear regression. And this is a good example. You have here in the x-axis the percentage of color of individuals in a country with college or higher education. Okay, and in the y-axis you have voter turnout. And what you see here is a positive linear relationship between the two variables. And okay, it's just an example of that. So in order to conduct bivariate linear regression, you need to meet some assumptions. The first one is validity. Okay, so your dependent variable needs to be numeric. That's the first and most simple thing. The second assumption is linearity. And you are assuming that one unit change in your independent variable has a constant effect on your dependent variable. And the size and sign of that effect is what you are really interested in to estimate, and is determined by the slope and direction of the line. Okay, that's linearity. Remember that I showed you in the past functions that are nonlinear, that are, for instance, quadratic functions, right? But in this case, we assume that the relationship between our variables of interest is linear. The third assumption is additivity. And basically what you're saying here, or the assumption that you have here, is that to explain the outcome variable, you can add the individual effects of all other factor variables. Okay? All of other, not factor variables, but all other variables of interest that are included in this, in the model. Okay? Notice that this addition or additivity also means that you can subtract individual effects. Like for instance, one of the variables is negatively related to the outcome variable, right? That's what I mean here. There are other set of assumptions that help us to conduct diagnostics of the extent to which the model is appropriate or is working correctly. And these assumptions, or these assumptions are related with the errors or the residuals. And the assumptions that you have in a linear regression is that the errors are independent from each other. Their variance is constant or tend to be constant, and that they are normally distributed. And this idea of the normally distributed is important because if they are normally distributed, basically they are canceling each other. Okay, but honestly, we don't have the space to talk about these assumptions, and it's kind of, to some extent, is a little bit complex. So if you have the chance to take another more advanced course in statistics, you're gonna probably learn more about these assumptions related with the residuals, that they are critical for linear regression. Okay. Okay, so for the estimation, we need to review part of high school algebra. So if you heard this famous phrase that like a high school maths is useless, that was a lie. Many of the foundations that you learn are used in all applied sciences and all statistics. And this is a good example of that, how linear function is useful here, because the linear function is the foundation of, to some extent, of the linear regression, the mathematical foundation. Okay. So just to remember a couple of things, this is a Cartesian plane. You have x on the horizontal axis and y on the vertical axis. And this is the linear function formula here. So you have y is equal to m times x plus b. So b here is the y-intercept. And this is the value of y when x is 0, right? Is here. And m is the slope of the line. So M tell us what is the inclination of this line, if it is going to be this way, or it's going to be this way, or it's going to be this way. And also tell us the rate of change of y relative to x. Okay? So if we want to know the value of y, we can use the information that we have available in this Cartesian plane. So we know that the slope, the y-intercept is 2 in this case. So when x has the value of 0, b is gonna be 2, and y is gonna be 2, right? Is this in this scenario? So in order to know the value of y, we need to know the slope. For that reason, the slope is the value of interest. Okay, the value that you want to estimate, because if you know the slope, you know the rest of the values of y. There's this formula, this very simple formula to estimate what is m, and in this case m is basically 1, so is the rate of change of y relative to x is 1 unit, and this is a positive relationship. Okay, in such a way you can know the other values of y. Well, it is basically the same in the linear regression, and we're gonna see how it's similar. But what's gonna change is the notation. And of course, the way to estimate this is much more complex because you have large data sets with a lot of information, okay? But let's introduce this example. Imagine that we want to know the relationship between income inequality and political stability, or the absence of social strife or conflict, okay? And we have this hypothesis. Countries with high levels of income inequality measured by this Gini coefficient tend to experience less political stability and more social strife than their more equal counterparts. So the Gini coefficient goes actually from 0 to 1, being 1 the highest level of inequality and 0 the lowest level of inequality. And the index of political stability actually goes from -3 to 3, something like that. But let's assume that it goes here from 0 to 100. Okay, being 100 the more stable country, and 0 the less stable country. Okay, and we estimate the relationship, and we see this linear relationship between the two variables. Okay, so as I said, the estimation of this of the linear regression is very similar to to the slope of the line and to this linear function. Notice that the formula is almost the same, but you have a different notation and you have a new element here. Okay, so alpha is gonna be the y-intercept, and similar to the intercept in the other case, basically it tells us the value of y when x is 0. So in this example, we're saying that alpha takes the value of 70 when the Gini coefficient takes the value of 0. So a country that is perfectly equal tend to have high levels of political stability in this mock example. Okay. B is our parameter of interest and the parameter that we want to estimate. Okay. And it's called beta in Greek. And basically, beta tells us the magnitude of the effect of x and y, and also the sign of the effect. If it is positive or negative, is the same role of the slope of the line. Okay? And the new element in this formula is error. So we're gonna include in our formula the residuals or error. And what is error here? Error is the difference between the observed value of y. For instance, imagine this country is, I don't know, United States. Okay? Oh no, Costa Rica. I don't know, something like that. So Costa Rica is a very stable country. It's kind of outlier. But it is the difference between that value, the value of Costa Rica, and the predicted value of Costa Rica if everything were perfect and linear, perfectly linear, or it's basically the prediction that the linear regression does. So Costa Rica should be here if everything were perfectly or fit perfectly to the linear regression. Okay, that's the error, and it's the error because, as you can see, these countries, for instance, are closer to the line, so the error here is going to be smaller, and Costa Rica in this mock example is very far from the mean of the line, or is very far from the line, so you can see a larger error here. Okay. So that's the residual, and you include that information to the analysis. Okay? So there are different formulas to estimate the linear regression, and we're not going to focus on that because the mathematics of this is kind of difficult. But it's very similar to what we had in the past. So we have here, for instance, the countries, we have the index of political stability, which is our dependent variable, and we have the Gini coefficient, which is our independent variable. Okay, and the most common method to estimate this is called the ordinal least squares, and you can see here that is not very simple. And basically, what you want to have here is to diminish the errors, the potential errors in the estimation. Okay. For that reason, the linear regression is also called the best unbiased linear estimation of the relationship between your dependent variable and your independent variable. Okay. There's another way to do it that is with the matrix form of OLS, and again, it's not simple at all, and it's not necessary that you learn this because R can do it for you, Stata can do it for you, and any statistical package can do it for you, but it's good that you know or have some idea of how this is conducted. And I know that Pollock teaches you to some extent how to conduct this manually. Some people make a lot of effort and emphasis to teach students to conduct these kind of estimations by themselves, but I think it's not the most useful thing right now. Okay. Another way to estimate the linear regression is with the maximum likelihood.